Okay, we're moving on. So GANs. So the whole idea of GANs was to be able, this is like a generative model as well, but it's kind of using a game theory technique, which is like a kind of like a zero-sum game, which try to min-max your function. So the idea is like you have a generator and discriminator. So the idea is you have two players here, the discriminator and generator. The generator trying to given a prior that one can be exactly like the thing that we have seen for VAE or AE, which can be a mixture of Gaussian or anything. You're passing to the generator, and then here it will make an image. You can see it as a decoder of autoencoder actually, which given an embedding will generate an image. The discriminator you can kind of see it as an encoder, which means given an image, it want to map it to one dimension, and that one dimension is if it's real or fake, something like that. But these two are kind of fighting each other. It's like a game. This one trying to make a real image, and this one trying to tell the difference between a fake one, generated one, or a real one. And in that process of playing, the generator will get better and better, and the discriminator will get better and better as well. So you kind of, so you're freezing the discriminator, let's say, trying to fool the discriminator by making a new image, and then you're freezing that, and then you're trying to kind of learn the discriminator, but by be able to tell the difference between these two. So you're switching between them and trying to make both of them to be better and better in every single iteration of the training. So that's the whole point. That's what I'm saying is like a adversarial technique is like a, it's not just one training, it's like a kind of like a two training things. Freezing that one, train the other one, freeze the other one, train this one, and trying to make the whole thing better. And they're kind of competing each other. And at the very end, you will have a generator which can actually make an image, maybe based on some prior, which can be anything. Can be noise, can be GMM, can be I don't know, any prior distribution that you want, or it can be conditional. And then here we should be able to tell the difference between these two. So conditional is instead of just using a random noise or a prior, you are adding some information about the data as well. So it means instead of just saying this is sample, this is one sample generated, you're saying that this is class number 1, this is class number 2 generated. So then you're kind of making the generator to generate a sample which is from that class. So then it means like if you have lots of image from face of lots of people, the generator trying to generate an image. It can generate an image from, I don't know, a male or female or anything. But let's say you want to actually generate a female male. You can enforce it. The only way that you can enforce it is kind of by adding a condition here, saying that, see, this is male, this is female. And the discriminator know that one as well. So you should be able to generate an image which matches the class. So the discriminator will say, yes, you kind of fooled me. I couldn't tell the difference between these two. So it kind of like adding a condition for the generator to be able to generate something that you are interested in. And here we are using the kind of the same technique, and the condition is the actual input. We're just saying that given the image, generate the image again. And then we have a discriminator here. The only job that the discriminator has is to tell the difference. Or if you want to look at the other side, you can just say that you have autoencoder. Back then, me as a human was trying to tell the difference between the generated one and the input one. How? I was defining a matrix, and that matrix could be any kind of distance metric. Could be Euclidean, could be cosine similarity, could be anything. I was the one defining the distance, and then I was using it as a loss. But then they said, why should I do that? I can have a discriminator, which the only job would be to tell the difference between these two. If the autoencoder can generate an image which is super similar to the input one, it will be able to fool the discriminator. So it's kind of like a plane as well. Generator want to make it better to be able to fool the discriminator, and discriminator trying his best to be able to tell the difference between these two, the input and the generated one. So you're kind of assigning the job of telling the difference to a model instead of a human. That was how they managed to kind of generate more realistic image, because instead of me computing distance, I'm letting a discriminator to do that, so the discriminator can actually find different maybe point in the image or in your data which I couldn't kind of come up with using some just distance metric function. So there are different way of doing that. Is like either so Autoencoder, the Anomaly, which using different score for that. And I kind of uploaded all this paper in the directory, so you can actually read all this paper to see how all of them has been implemented. They are kind of I guess they're all open source as well. There are lots of code for them available, I guess in TensorFlow or PyTorch. You can see them and you can see how can you implement them and how can you play with them. So all the code are available as well. So as I said, the hybrid one is you're just using, let's say, autoencoder. You're using the embedded layer, like the representation one, and then you're using any kind of model that you want. It can be any kind of KNN, clustering, or any model. You're just using the embedding layer. So then it's like, then you can kind of see the autoencoder one as a dimension reduction techniques. Instead of PCA, you're using autoencoder. And even if you want, you can add your own constraint to make it to be like a Gaussian or anything you want. And then you're using it for other models like KNN, clustering, or any technique you want. And that's the whole idea. So let's get back to the notebook. And I guess I should crazy.
Can you make the?
Yeah, I'm trying my best here. Yes.
So for say if you have a text, right? So if you use an autoencoder to embed the text, will you be able to catch the semantics in the embeddings that is generated from autoencoder?
You're saying that if you use the text, will you be able to catch the semantic of all the, let's say, all the information in the text? We can say that if you use a sequence, then you're probably using a window, or you're using an RNN or LSTM model. And then the only thing that you're doing is you're mapping it to a vector, and from that moment you want to kind of, it's like you're compressing all the knowledge in that sentence in one vector, and then you want to generate the sentence again. They're kind of using the same technique for translation, actually. They're saying that the input is, let's say, English phrase, the output is French, let's say, and then they're using the same technique. But here, instead of translation, you're translating to your own language again. So it's like it can be RNN-based autoencoder.
So the input sequence and the output sequence is identical, right?
Yes, exactly.
So then what we are doing then is that middle part, like the last latent vector, will it like for say then we only retrieve that latent vector, and then we for say map all the different sentences that we got from all these vector, and then we plot it. Will like the sentences that actually have similar meanings
yes.
be clustered together?
Yes, that's the goal. Yes.
Thank you.
So here, I want to start the session by importing everything. Here I'm kind of using the synthetic data as well, but I won't use it that much. I will mainly use MNIST here and credit card fraud again, because to be able to compare with whatever we have seen from the previous session. So some function, which one of them was evaluation that we have seen from the last session, and visualization. So the model. Here I have implemented a bunch of models that you will use them during this session. First of all, I've used Keras here. We can use PyTorch or whatever you want, but kind of the idea is almost the same thing. It's like you're adding a bunch of layer, and then you have your own neural network. here I have made that function which given a list of widths of layer. It will make that neural network for you. So I'm defining an input layer using the first number, and then in a for loop I'm using all the other number to make a dense layer with that size, and activation will come from the activation parameter, and then I'm using the output layer which I will use the last number, and the final activation which can be anything, and then you will have your model. So then we will have a simple neural network model using Keras. So you can have more layers, you can have different width, and it is as easy as that, just using that function. So the other one is the autoencoder that you will play with, which basically is kind of having that neural network at the very beginning and the reverse of it at the very end. So I'm using the same list again, but for the encoder part, as you can see, I'm just adding all the layer, and then for the decoder part, I'm doing the reverse of the list to make these autoencoder. And to actually show you how it works, here I'm loading the synthetic data norm, which I've seen before, and then I'm making autoencoder. So here the input layer, the input size is 2 because it's 2-dimensional, right? And then I'm just saying that map it to just 1 dimension. So, and then I'm just saying that make the model. You can say compile. Once you say compile, you're saying that what's the optimizer. I'm using Adam here, and then you say what's the loss. I'm saying that is binary cross entropy. It can be anything actually. And then you're doing the fit. I said number of epoch 30, batch size 5, shuffle true, and that's the whole basic thing. And then I'm just saying that okay, then that will be my model. Here I'm predicting the output of it. So the prediction of the input should be exactly kind of the input as well, right? Because that's the reconstruction part. I'm computing the difference, which will be the loss. So that's why this one will be the loss, doing the mean. And then I'm doing the visualization. So as you can see here, I pass layer 2 and 1. The autoencoder, the first layer is 2. The middle layer is 1. That's the embedding layer. And then the output layer is 2 again. So I'm kind of reconstructing it from one node, which is a middle layer. And then that's the training part. It's trying to train the model. And then I just said here, I said that visualize it. And as a threshold, here I said use the mean as a threshold. If anything is more than the distance and the loss, the distance between the input and output is more than the average of all these distance, maybe that one is outlier. And actually it is working for me to be able to find all these anomalies in my data.
So when you train it, when you compile it, it says that your loss is binary cross entropy. Mm-hmm. But when you predict, it's the square loss, right? So are you actually fitting with which loss are you fitting with, and why? Why, if it's the binary cross entropy, then why?
Exactly. So you can use whatever you want. And I should have used MSC. We can do that as well. So you're right.
I'm surprised it works, like, because this isn't a binary variable, right? You're actually in 2D.
Okay. MSC and the cross entropy, both of them are a way of maximizing the likelihood, right? So both of them trying to maximize the likelihood. MSC just the assumption is the sigma. So it just the assumption is you're doing the regression and just saying that the sigma is 1, the average is the output, compute the distance, what is the likelihood of it, and if you compute it, it will be the square of the distance. The log probability is kind of the other version of. So both of them are actually optimizing the same thing, but with different view. So that's why even if you use the first one, do the second one, even if you want to do the binary classification, you can just use MSE. So it means then you will try to say that the distance from 1 and distance from 0. Or you can just use log prop. So both of them will try to do the same thing, but maybe by different view and different scale of the loss, I would say. But you are right. If I was trying to compute it using MSE, it would be better to just use, let's say, MSE here as well, and just train it again, and say that okay, maybe that will be a better version of it, maybe.
While it is training, could you go through again? So where are the encoder, where are the decoder parts?
So here, as you can see here, so here, see, almost I got the same identical result. So my encoder is like from 2 to 1, and the decoder is from 1 to 2. So it's like just.
Could you show this in the code?
Sure.
What pieces?
So the encoder part is that part, and then that's the decoder part.
Okay, so there is. You don't pull latent representation from the model,
No.
do you? Okay.
Because like if you want to do any kind of generation or do any hybrid model, you can extract it and reuse it. Here my goal was just look at the reconstruction error, and use it as a score for final outlier in your data. So for this session, for final outlier, you don't care about the embedding. But if you actually want to do any kind of other tricks, like I don't know, doing any clustering, visualization, I don't know, any kind, generating any embedding, yes, you better extract it and reuse it for other tasks. Here we are not doing that because we are not interested in it.
Sorry, I didn't watch the video before, but so if I fits in. So, can you say the mechanism that how can you use reconstruction to identify anomalies?
So the idea, okay, I'm just going to say it short. The idea is, if your data is clean, the model will try its best to be able to compress it, and then be able to decompress it again, and to be able to have exactly the same identical output as your input. If you get a good score here, so you say, okay, you got the loss was less than something, and you say that the model was successful to be able to compress it and then decompress it, then you say that the model kind of has learned how it can compress your data without having that much a loss. From that moment, if you have a new sample, which is different from the thing that you have seen before, the assumption is because of that difference, the model won't, even if the encoder will map it to a point which is different from the others. And if you use that point in that embedding for reconstruction, the thing that you will reconstruct won't be similar to the input. So that's why the distance would be higher. And even the other thing is they're saying is like that. Even if you, then it means, let's say you have an image, you just add a big circle at the corner. There was no image with the circle at the corner. That's why when you're compressing, the model will always ignore, let's say, whatever is in the corner. So when you're reconstructing, the reconstructed image won't have that circle in the corner. So that's why the loss will be high. And even based on the difference, you can say maybe which pixel or which part of the data will cause that maybe anomaly in your data. So just gonna move fast. So that's how I just use it here. But here, then I'm gonna do another set of things. For anomaly, just make my model to be a bit harder. For MNIST, here I said number 7, 8, 9 is anomaly. The rest is normal. Instead of just saying 7, I said all these 3 are outlier, the rest are normal image for me. Try to kind of find a difference. The other thing is, this is image. I better use, as I said, CNN model, which means they will be able to capture some spatial relationship in your image. But here, I'm just saying that that's image, get each row, attach it together, make a giant array, which the size is 784. So I will lose all the relational information between the pixel, because I just want to make it to be simple. And then instead of using CNN, I'm just using like a regular neural network. But for your own things, if you're dealing with image, you better just just use the image as is and use a convolutional neural network. So here I'm saying that, okay, that's the autoencoder. I just made the model. See, the first layer is 784, and then 30 and 10, and then again the reverse, 30, 784. That's the autoencoder. But you can change the size. You can make it to be anything, and then you can have any kind of even you're right again. I should kind of make it to be MSE as well. But still, the assumption is the result will be almost similar.
So then, in this case, then the autoencoder should not be as robust as GAN, right? Because if like you actually input a fake thing, like say image, like fake thing, which will be very similar to all those homogeneous data set, then when you go through the autoencoder, then the loss won't be too high, right?
If I pass what?
Like a fake image, like what you do in GANs.
Okay.
Then because it's, I guess the definition of fake is it's very similar to those other homogeneous real data, right? Then when you pass it into the autoencoder, you will probably not have a very high loss, right? So then you cannot detect it.
So the idea here, okay, the idea between autoencoder and GAN is a bit different. So the idea is just regular autoencoder is, the assumption is if you can compress something good enough that you can decompress it, then you have learned the data. And if you have used just enough parameter, not more than enough, something like that, then from that moment you kind of overfitted on your data, so you kind of learn the point, memorize them to be able to map them, and then to be able to decompress them. So if you've seen any point which is not similar to the data that you have seen before, the model should the assumption is the model will fail. So even for the MNIST, we see that not all the time, because here, as you can see that here the input is 784, and I just use one hidden layer before the embedding one that I care about, and the size is 32, so I'm losing lots of information, and then I want to decompress it. So maybe that parameter is not enough for MNIST. Maybe I should have used maybe more deeper neural network or more parameter to be able to learn the MNIST. That's why if I just use that model, it's just fit it here, and you can see that that's the loss. And then if I just say, okay, predict that one, and if I just say, okay, the thing I want to do is reconstruct. You can see the reconstructed one is not that different, but is not similar as well. So you can say, okay, here, 1,1,0,0,4,4, 7 supposed to be like Anomaly, but the model still has some idea about it. For 9, so the model kind of was confused maybe, because it hasn't seen it. So for us, it was outlier actually, but maybe for 5, still it was not that much certain about it. So as you can see, even by completely ruining the whole structure of image and just using as an array and just using a small neural network and basically just for autoencoder, we managed to reconstruct the image. So
autoencoder needs to train on clean data, right?
Yes. Even if the data is not that clean, there will be like a noise in your neural network, which the neural network should be able to handle it. But if you have like a systematic error which lots of anomalies are close to each other in a point, then yes, it will destroy your model as a model for finding out for outlier. So the assumption is yes, the data should be clean. So that's why you're overfitting on that clean data, kinda. And then you want to say that if the model will fail on a new data that you haven't seen before.
Thanks.
And then here, the thing I want to do is like, okay, I just want to say what is a threshold, maybe. So I'm just using the score, the distance, and then I'm just computing the max one. I'm just saying, okay, the max distance between them was maybe 0.12. And then here, the thing that I want to do, I want to visualize it between the normal one and the anomaly one that I generated. As you can see, because all those images were super similar to each other, to be able to discriminate them for the model was super hard, just based on the distance between them. So that's why the model was not able to do that here. See, lots of them are here. But as you can see, if you look at the tail, all the thing kind of more than, I would say, 0.1 are basically the outlier for my data. So maybe having 0.1 as a threshold is the best thing. I just visualize it, and then I just come up with this threshold. And even for a threshold, you can have it even lower to be able to capture all these, it's not here or not. You can just put it here to make sure whatever you're predicting is actually true. And then you can kind of compute the score for it and then see what is the performance of the model. Here, as an first exercise, I want you to actually do the same thing for credit card. Okay, I'm just going to give you some hint as well. You cannot use it, but you can use it if you want. To make sure that all of you can actually do it, I have the code here as well. But because if you don't want to kind of redo the whole things, but my idea is play with the number of, number of layers or anything that you want to see which one will give you the best result. Here I have run it before and I got some result. So you can play with that as well. So back then for credit card, see, it was a lot better for credit card data because it is not like image, that even the number of dimensions was just 30. So by just a small autoencoder, you can kind of capture all those outliers. And then you can just use the evaluation here to get f1 score, which here the f1 score was almost 4. The thing that for the first exercise, you can play with the model, use different number of layers, or you can change that one to MSC or keep it like that, but to see which one will give you a better number for credit card information. And that's the first exercise. 15 minutes, 10 minutes. Here or?
No, on the graph, the chart. Yeah, this one. So what does it say?
This one?
Yeah.
This is the MSC for different sample. I made it for the credit card normal and fraud. So for the learning part, I'm using the data itself, but here for kind of doing the making the chart, I'm just saying that for the normal one, make the first one, which is like a purple. For the anomaly one, make it to be like an orange, and just give me, it is like a histogram for different, let's say, MSC distance between the input and the output.
Mm-hmm. And so basically, for all the test cases,
so it means once I learn the data itself, from that moment I could just use autoencoder and say the distance is a metric for me. So I'm missing lots of things as well for sure. There are lots of points here as well, but I can just use any threshold to kind of be able to be able to tell the difference. So the thing I'm asking you to do is try different number of layers, or any optimizer that you can change it, or you can just use that one or switch it to MSE, using that I tried. You can play with the number of epochs or number of batch size, all these number. Then you will have a new autoencoder that you will see here. And then if you run that one, you should be able to see the result of your model. And then once you run that one, you will see what's your F1 score. So you can play with these hyper numbers and see which one will give you better score. And you can post it in a Slack if you want.